Okay, so I want to talk a little bit now about, this is the sort of last topic of the unit, and it talks about independence and how to prove whether something is independent or not. So let me just kind of model something here. If two events are independent, so if two events are independent, then one of these two conditions will be true, one or both. Then one or both conditions will be true. So the first condition is the following. Probability of A given B should equal the probability of A. If this is true, then A and B are independent. And this should make intuitive sense. If A and B are independent, that means whether B happens or not doesn't affect A's likelihood to happen. That's what independent means. B's happening does not affect whether A's happening. So the probability of A given B should equal the probability of A if two events are independent. The other option is the following. And again, remember, both one of these or both of them can hold. It doesn't have to be both. If either of these two statements are true, so the second statement says the probability of A and B equals the probability of A times the probability of B. We've been using this for a lot of problems that gave us two probabilities and we just assumed they were independent, but today we want to talk a little bit about kind of proving that. So if two events are independent, one or both must be true. One or both must be true. Shamar? Giselle, is it down, I guess, a couple degrees? It should kick on then on its own. All right, so this is one or both of these must be true. And now, we talked about this already, but let me just remind you, for mutually exclusive, I'm sure the air will kick on here in a sec. For mutually exclusive events, this must be true. The probability of A and B must be 0. Because if they're mutually exclusive, they can't possibly happen at the same time. We discussed this last week. And the other thing I know has to be true, we discussed this, but let me just review it. A or B is probability of A plus probability of B. I don't need to subtract this because this is 0. If two events are not mutually exclusive, remember we subtract this area because we don't want to double count. But if they're mutually exclusive, there can't be any double counting because they never happen at the same time. It's as if the two Venn diagrams never intersect. Mutually exclusive Venn diagrams look like this. Here's one, here's the other. They never intersect. This is mutually exclusive. Mutually exclusive. So let me stop. There you go. Let me stop and see if there are any questions on what we talked about here. Yeah. Sorry.
Okay, so if you plug in the numbers for A and B, then that will be
Right, yeah. So if you show that probability of A times the probability of B equals the probability of both, then you've proven that A and B are independent. Or if you do the top one, then you've proven it. You don't have to do both. Okay. So let me kind of walk through some of the mathematical proofs of kind of why this works. So, let me walk through the following. If I say the probability of A given B, the probability of A given B.
And that's still mutually exclusive?
No, this is now, I'm going to prove these independent rules. I'm going to prove these two independent rules.
Do that on that side.
We're getting too little space. I'm going to prove the independent rules here. So we know from our discussions in the past, the probability of A given B is the probability of A and B over the probability of B. Yesterday we said that the event that comes after the given goes downstairs. I think that was the rule we kind of established yesterday. So now, probability of A and B is just this, if the two events are independent. So I'm just going to replace this with this right here. So I'll have probability of A times probability of B, all divided by the probability of B. And now we have the cancellation. So there we have shown that if two events are independent, then the probability of A given B is the same as probability of A. That's just the proof of this right here. Let me stop and take questions on anything so far, the rules or the proofs. Shemaya. Yep. No, this is proving the rule. Yeah. Now I'd like to prove. Yeah. Okay. Now I'd like to prove the following thing. This is something that you read in the textbook and we discussed before, but I want to prove this now. Does anybody? I still need this blue. Yeah, the blue. So, what I want to prove now is the following statement. And we discussed this in like week 1 of probability. We said if two events are mutually exclusive, they cannot be independent. Independent. We said if two events are mutually exclusive, it's not possible for them to be independent. Because if they're mutually exclusive, that means if one happens, the other one won't happen. That can't be independent, because then independent says one event happening has no effect on the other event. But mutually exclusive, if one event happens, the other event can't happen. By definition, they depend on each other. And let's prove why this is the case. For mutually exclusive, events, the probability of A and B equals 0. For mutually exclusive events, the probability of A and B equals 0. That we know. That's a fact. Can't possibly be anything else. They can't happen at the same time. And we just said that for independent, the probability of A and B equals the probability of A times the probability of B. We just said this is true for independent. That was rule number 2. We said this is true for mutually exclusive. That's a fact. So if a mutually exclusive event could be independent, then this has to equal this, which would look like this. This is not possible unless one of the probabilities has a 0 chance of happening, right? Which is a trivial case that we'll never discuss. Like you would never have a probability of something having a 0% chance. It doesn't even make sense to discuss it. There's no probability. It's just going to happen, and the other one's not going to happen. Yeah, so this is a rule for independent. This was the second rule that I wrote in blue earlier. So we said for independent events, the probability of A times B is the probability of both.